The main topic of this project is about attaining zero waste for Malaysian chemical process industry. Following the requirement, we chose a wastewater treatment industry while critical analysis are done on reverse osmosis system implemented with a process control. In this presentation, we discuss on the process flow of wastewater treatment industry, process control that involve in the RO system, challenges that reduce the efficiency of RO process, and recommendations suggested to improve the system.
What is wastewater treatment? Wastewater treatment is a process used to remove contaminants from wastewater and convert it into an effluent that can be returned to the water cycle. Physical, biological, chemical, and sludge treatment are the four most popular methods for treating wastewater. Because of its cheap cost, one of the physical water treatment technologies, reverse osmosis, a pressure-driven membrane process, has been widely employed for the treatment of municipal or industrial wastewater. Reverse osmosis differs from filtering in that fluid flow is accomplished by osmosis over a membrane. Waste disposal from wastewater treatment industry is increasing due to rapid population growth and economic activity. The disposal of this material continues to endanger the ecosystem. The control system is an essential component of any process, but environmentally friendly implementations are not commonly available. Certain aspects of process control systems have resulted in some key gaps in the effective and efficient regulation of the process from both a theoretical and practical standpoint. The three objectives for this experiment are as follows. 1. To investigate the type of control system used in the reverse osmosis process and to justify the use of a control system with environmental and chemical engineering components. 2. To investigate the difficulties associated with the use of process control systems in the chemical sector. And lastly, to investigate an efficient waste control systems in the reverse osmosis process.
Wastewater treatment begins with collection of sewage. Firstly, the sewage is screened, separating it into wastewater and sludge. Wastewater is firstly treated by removing the suspended solids in two steps: sedimentation followed by fine filtration. Then coagulation and flocculation are initiated, and the resulting flocks are removed. Next, biological processes of microorganisms will degrade the dissolved pollutants. Solar evaporation is then employed in order to collect clean water vapor. Any harmful pathogens remaining are eradicated by ozonization. Reverse osmosis is the final treatment step to produce reusable water. Treatment of solid waste and sludge starts with conditioning, a process in which colloidal content is reduced and water is separated and removed. Thickening then takes place where more water is driven out from the sludge. Next, it undergoes stabilization, where its persistent amount of pathogens and overall volume is reduced. Microorganisms then decompose the organic matter in the sludge to produce biogas and biomanure in a process called digestion. The remaining solid is incinerated, producing large amounts of heat and carbon dioxide. This is used to generate electricity, and pressure produced from the carbon dioxide gas is used to move turbines. This carbon dioxide is then extracted and sold to other industries, leaving behind clean air. Meanwhile, fly ash and bottom ash from incineration process can be sold to construction companies as raw material.
Next, we will be discussing about the control system. This figure shows an integrated system of ultrafiltration process with the reverse osmosis process, where the feed of the ultrafiltration is pumped from the screening section and the filtered water will be sent into the UF tank before it pumped again as feed for reverse osmosis system by the RO booster pump and RO high pressure feed pump. At the end of the process, two streamlines produced, which are RO concentrate and fresh water. As shown in the figure also, there are two proposed control systems, which are flow rate control system at the RO feed stream and pressure control system at RO concentrate stream. Here is the overview of a reverse osmosis control system, which include the control variable and manipulated parameter for the proposed control system.
Next, we are discussing the challenges faced in the process control of the reverse osmosis system in wastewater treatment. The first challenge in RO system process control is the membrane fouling. Membrane fouling typically occurs under four conditions. First, biofouling is referred to the microbial growth on the surface of the RO membrane that leads to lower membrane permeability and higher pressure drops. Next, scaling occurs due to high level of precipitation of materials such as silica and phosphate on the membrane that minimize the productivity and permeate quality. Organic fouling is the addition of organic compounds that are available in wastewater on the membrane surface that results in declining flux. Finally, colloidal fouling is the formation of cake layer on the membrane surface due to accumulation of particles. The next challenge is the high cost of reverse osmosis system, which is mainly contributed by the high energy consumption and membrane replacement. Energy consumption takes up to 38% of the total cost, while membrane replacement takes up to 3% of the total cost. The final challenge is the disposal of sludge, which is a byproduct of the RO treatment system. Generally, the only available option is by disposing the sludge in sanitary sewer. However, the process is considered difficult due to the complicated permit acquiring process. Moreover, inefficiency in sludge disposal will create a disturbance in the system while simultaneously increasing the cost of the RO plant.
Moving on, we will now discuss about recommendations that can be done as improvements to the challenges faced in the process control. The first recommendation is by implementing cascade control. Cascade control involves the use of two controllers, with the output of the first controller providing the set point for the second controller and the feedback loop for one controller listening inside the other. Hence, it will provide better response to the disturbances. In cascade control, the controllers have to be tuned to the most optimum tuning parameters to provide better results with minimum oscillation, less luggage, and less time needed to reach the set point. Cascade control also fully eliminates offset, which will then provide smooth flow to the RO membrane surface and minimize membrane fouling. Another recommendation that can be taken into consideration is by using ultra-low energy ULERO system. In ULERO system, the membranes use less pressure, which is 60 to 80 psi compared to conventional RO system, which uses at least 200 psi. Since the pressure used is much smaller, the set point is also much lowered. Thus, the process will not require as much energy to reach it once any disturbances occur in the process. Other than that, the membranes for ULERO system are smaller than conventional RO system, but with better recovery rate. Since the area and pressure for operation is much smaller, this will reduce the cost for operation for the system.
In conclusion, all objectives of the project have been successfully achieved. Throughout the discussion, we managed to determine the efficient waste control system in reverse osmosis process, which involve pressure and flow rate controller in a feedback loop control. Besides that, we also detect and explain the limitation of the system, such as membrane fouling and its high cost. Implementation of cascade control and ultra-low energy RO system are recommended to improve the process.